it's logic related to elliptic curves and their rational points. It's a continuation of the first lecture, but I'll sort of backtrack a tiny bit so as to make it a sort of self-contained if anybody has missed the first lecture. And when you make it self-contained, you also sort of, in some sense, I want to increase the thickness of the description of some of the history of logic and its relationship to elliptic curves. But I'll begin from the beginning again. Recall the motivation of Maciejewicz and how elliptic curves might enter the picture. Now, as from last lecture, Maciejewicz was the person who showed that Hilbert's 10th problem, exactly as it was stated by Hilbert, has a negative solution. And he did it in the very positive way of building up a Diophantine definition of every listable set. And so that could be thought of as negative if you want, or it could also be thought of as extremely, extremely positive, showing the richness of Diophantine, so to speak, language. And the way you build it up, if you haven't done it yourself, you can sort of begin today. So you could start by noting, and most people do start by noting that the set of positive numbers is Diophantine. Thanks, for example, to Lagrange's theorem that says that any positive whole number is expressible as the sum of 4 squares. And of course, the minute you do that, it follows easily that you have not only positive numbers greater than or equal to something, or numbers less than or equal to something, with a sort of a slight shift of sign of the equation. And you can take the combination of the two equations to any finite subset of Z as expressible in a Diophantine way, and the complement as well. So little by little, you build. Already we see that the issue of being Diophantine is sort of as a rough-hewn notion, in the sense that you can add or subtract finite sets at will. You can work a little more, let's say, in elementary ways to establish that arithmetic progressions are Diophantine, sets of squares, cubes, nth powers, that sort of thing, composite numbers. The reason why I put this in blue is that it's going to be an important turning point, if you wish, of the building of Diophantine vocabulary, if you want, for any fixed integer d. If you consider the integers t that are solutions of that Pell equation, you get that it is also Diophantine, and the parenthesis is important, that this being a set that grows roughly exponentially. That's going to be a theme, and we'll get to a tiny bit of the history of the subject to indicate what an amazingly rich and complex theme it was. Factorials, now there, you have to begin to really work. There is a system of polynomials that cut out the set of factorials. I might even have, if I had the courage, give you that system of polynomials, but it's no mean trick. And you do this in steps by showing that binomial coefficients, for example, have a Diophantine description. And then you play with the following totally unpromising, you would think, formula, that the factorial is a limit of n to the m over a concoction made out of binomial coefficients, and somehow you deal. Now that's part of the legacy of the subject, how they do that. And the subject, as I hinted, has an enormous history. For example, it begins, and it must have begun in the negative aspect of it. That is to say, the positive aspect of it was Hilbert in the early 1900s saying to devise a process that actually solves polynomial equations over the integers. But the negative search began in 1944 with Emil Post, who plays a major role in the history. I won't sort of get into that aspect, but he does play a major role in it. And he simply said, it begs for an unsolvability proof. It essentially proceeded almost continuously from 1944 to 1970, when Maciejewicz clinched the theorem, that is to say, proved that it was unsolvable. 3 decades. Now, from 1944 to 1960, which I won't sort of even bother to put a slide on, because if I did, it's such an exhaustive and such a beautiful story, I wouldn't finish the entire hour just talking about it. The early attempts managed to show that if you enrich the Diophantine language with an exponential function appropriately, you could then describe or obtain by Diophantine exponential function all listable sets. And in the interim between 44 and 60, people were sort of playing with sort of making the issue of the exponential function less and less important and replacing it by sort of more and more approximates to the exponential function. At one point, there was an approximant that if you could get that, and if you knew, curiously, if you knew that there were arithmetic progressions having prime numbers of arbitrary length, you were in pretty good shape. You were in maybe better shape. You would, I'm not sure that you would have actually solved it, but you were in better shape. And so there's a whole, let's say, sideline of the history having to do with finding very roughly exponential functions. But it was in 1960 that Julia Robinson, established the very, 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 very roughly exponential axioms that one needed in order to be able to list all, define all listable sets. And these are the axioms. You want to have a set of couples such that AB, such that the first entry is in some reasonable way bounded by the second, and the second from below, and the second is bounded from above. The first is bounded from above by the second, by some reasonable function of the second, and the second is bounded from below by some reasonable function of the first. And that stands for an exponential function, or a very roughly exponential function. And if you could do that, all listable sets would be Diophantine. It was 1970 where Maciejewicz actually provides a definition as required by Julia Robinson. He took his collection to be the collection of pairs AB, where the B was a Fibonacci number and the A was essentially an index of the Fibonacci number. And he managed, you could do that, and you could easily show that it satisfies Julia Robinson's conditions, but there's work also to show that this is definable in a Diophantine way, and he did this thereby completing the proof. Now, most of the time, when people say, this is how I proved the theorem, you know, first, it's usually short. And sometimes it works, sometimes it says, oh, okay, I understand how I did it. Here is Maciusewicz's quote. I'm going to read it. It's long, which I think is the most illuminating simple description of the sort of, how to put it, the preparation of thought that he wanted to have before he actually proved his theorem. He didn't prove his theorem the way he described, but he gives a sort of a pre-preparation for how he's going to prove the theorem. Okay. The idea was as follows, writes Maciusiewicz. A universal computer science tool for representing information uses words rather than numbers. One such method is naturally related to Diophantine equations. Namely, it's not difficult to show that every 2 by 2 matrix with the mi's, with the m's being non-negative integers and the determinant equal to 1, can be represented in a unique way as a product of matrices. The matrices that have been displayed there. It's evident that any product of such matrices has non-negative integer elements and the determinant equals 1. This implies that we can uniquely represent a word in the 2-letter alphabet, M0, M1, by the 4 tuple, the mi's, such that the numbers evidently satisfy the Diophantine equation as displayed. Under this representation of words by matrices, the operation of concatenation of words corresponds to matrix multiplication, and thus can be easily expressed as a system of Diophantine equations, opening up a way of transforming an arbitrary system of word equations into equivalent Diophantine equations. Many decision problems about words have been shown undecidable. So it was quite natural to try to attack Hilbert's 10th problem by proving the undecidability of systems of word equations. There, again, there's a kind of bootstrap. There was the issue, there is a sort of a kind of an undecidability that he's going to bootstrap to. And of course, when he does, he shows undecidability of Diophantine equations in Z, and from there, one has a whole, how to put it, we have a whole culture of bootstrapping to get sort of finer and finer results from his. Okay. Now, and what he uses is Pell's equation. Well, specifically in his first proof, it's Fibonacci numbers. And the Fibonacci numbers are coefficients of the groups of units of a certain famous real quadratic field. There's the golden mean. And they are the solutions of an equation y squared minus dx squared equals plus or minus 1. He could also use various norm equations and understood that he could. But the bootstrap method, to go from the integers, as we talked about in the first lecture, to any larger ring, depends upon two things. Well, it depends upon first knowing that you have something in the smaller ring, that is, say, undecidability, and being able to convey the issue of undecidability of the small ring to the large ring. Now, how might you do it? You might do it as I put on a slide, but didn't really talk much about last time, by actually defining the smaller ring in the larger ring. Just find a Diophantine description of the smaller ring and the larger ring, and then you've transported anything, any decidability issue, any decidability algorithm that you would have for the larger ring would immediately transport to the smaller ring, and then if you knew the smaller ring was undecidable, that would show there's nothing like an algorithm for the larger one. Okay? Well, that is very often too precise. Instead of defining the ring, you could define what the logicians call a definable model of a subring of A in the vocabulary of B, and it does the same thing. What is a definable model? It's just a set theoretic injection, not a ring theoretic injection. A set theoretic injection of the smaller ring, not even in the larger ring, but in some power, some fixed power of the larger ring. And that has to have the property that the image of 1 in the smaller ring is definable in the larger ring, and the graphs of addition and multiplication similarly. And then you say that the big ring, B, has a definable model of the small ring. Now, if a ring has a definable model, we then get, as I said, undecidability implications. Now, just recall from the first lecture that definability comes in various strengths. We can have Diophantine definability, that is, say, just by Diophantine equations. The logicians would say just by existential quantifiers. Or we could have sort of more, let's say, more fluid types of definability, such as first-order decidability, where the sentences might contain there exists for all, there exists for all. But in any case, if B has a definable model of A, if you know that B is decidable, you know that A is. Now, the problem with Pell's equation for the bootstrap method is if you want to pass from ring A to a larger ring B, let us say when you consider equations of the form y squared minus dx squared is plus or minus 1, you often get more rational solutions in the larger ring. It's a kind of fluid ring, and in some sense, the set of rational solutions in B of the same equation has completely forgotten about this poor subring A. And this is where elliptic curves enter the picture. Okay. Now, there's a development here, and I've somehow collapsed it into one theorem, and I'll tell you perhaps its stages. These are theorems of the people listed. Suppose you found an elliptic curve E, say over Q, that has infinitely many rational points over Q, and the Diophantine stability property of last time. That is, say, the Q rational points are the same as the K rational points. Then the set of rational integers is Diophantine over OK. I'll give you a sort of a closer view of why that might be in a few minutes. And of course, Q turns out to be a little irrelevant, but irrelevant in the sense of the result, but not in the sense of the techniques of the proof. So you can climb number field extensions. By number field, I mean fields of finite degree over Q. So let K and L be number fields. And the same thing is true. That if there exists an elliptic curve over K having infinitely many rational points over K, and the Diophantine stability property for that extension, then you've passed from OK to OL. Now, as I said, I was sort of collapsing a certain amount of the history of the subject. For a long time, one only knew this if the Mordell-Weil rank of the elliptic curve was 1. That is, say, the elliptic curve had a cyclic group of rational points, and the extension to general is something serious. So here, you don't need to know anything about the Mordell-Weil, about any structure of the elliptic curve, just that it has infinitely many rational points. Now here, I have a little aside in red. Let's say I should mention the stronger Lang conjecture, but I just had lunch with Bombieri. And I don't know. But that's okay. It's not my conjecture after all. Yeah. Okay. Think of it this way. I'm going to.
I heard you there. Did he not say that he disowns?
Yeah. Yeah. That's okay. But as I say, it's not mine. Okay. So here's a way of reformulating the Lang's conjecture in a manner that's related to this issue. Suppose you have any algebraic variety whatsoever that has two things: infinitely many rational points, and is Diophantine stable for some extension. Then the stronger Lang's conjecture would say there's an abelian variety, there's an image of an abelian variety in this or elliptic curve, in this larger variety, possibly, that has the same property and that you could use just as well as the larger variety. Now, the takeaway that I would have from this stronger Lang conjecture that is maybe is that that elliptic curves are absolutely essential for bootstrapping. Abelian varieties being their sort of high dimensional brothers. Okay. Now, that fact sort of reminds one that elliptic curves are in close contact with an immense number of different fields of mathematics, and the contact is sometimes related. I won't get into that in this lecture, but it is related in some, what I'm going to say in a second is related to what I've just said. For example, they have an essential role in cryptography that I think everybody in this room probably knows, and they have a certain predominance in that field that warrants publications such as this 1999 government memo. There goes. Recommended elliptic curves for federal government use. Okay. Well, actually, there's a certain amount of controversy about this memo, so if people want to ask me. And it is related to the discrete logarithm problem. The first page of that memo immediately focuses on the discrete logarithm problem and emphasizes that their preferred elliptic curves are sort of particularly difficult for that enterprise, we think.
Yeah, thank you.
Oh. Okay. Okay. Now a little few moments about elliptic curves, just to remind people that what are they? They're smooth plane cubic curves, and usually you have you want a rational point for them, and very often you put that rational point at infinity. So a smooth plane cubic curve with exactly one point at infinity can just be expressed as an equation of the form that's in blue in the middle of that slide. And so therefore, the only thing you need to describe that equation are the two coefficients, c and d. And just make sure that that cubic polynomial doesn't have multiple roots, and you're in business, you've got a rational curve. And so the C and D are just algebraic objects. You can think of them in any ring if you want, or you can think of them in any field. And so you have elliptic curves over any field. And the set E of K in the middle of that slide is the preferred notation for the set of rational points of the elliptic curve, specifically not the affine one, but rather the projective one. So you include the point at infinity, which you perversely call 0, and take all the affine solutions of that equation, and that's the set of rational points. Now we talk about Diophantine, and so one should mention for a moment the Diophantus himself. And it's actually, it seems to be the case that some readers of Diophantus find hints of what we call the coordinate tangent process for elliptic curves. I don't see it actually, but anyway, perhaps there are hints. He certainly was interested in cubic issues. And the thing about a cubic curve is, which has its sort of wonderful binary relation, that is to say, if you take any 2 points on the curve and run a straight line through those points, it'll intersect that curve and at exactly one other point. And so if the 2 points are rational, that third point will be rational over whatever field the elliptic curve is. And so you get a binary relation as depicted by these pictures. And you can do this either for 2 points, or you can do it as a tangent line and think of those 2 points as equal, and you still get such a thing. And you would get such a thing for any cubic hypersurface, any dimension, by the way. And I think the arithmetic of these cubic hypersurfaces is very understudied. I mean, there are a lot of questions, asymptotic questions that one could ask about higher cubic hypersurfaces having to do with their specific arithmetics. But anyway, when the hypersurface is a curve, you've got an elliptic curve, and that binary relation turns out to produce an abelian group structure. So that's the, in some sense, the crash course about elliptic curves. Now, in the era of Mordell, which is the 1920s and 1930s, and 40s, 50s too, we were sort of really in the midst of a lot of Diophantine questions about elliptic curves, and Mordell was very adroit at asking just the right subtle questions in the end to end up with a problem about elliptic curves. For example, the blue thing on the screen, what product of 2 consecutive integers are equal to a product of 3 consecutive integers? Okay, well, we can work on that. The answer, by the way, is 0, 6, and 210. You want to know the answer? And of course, the equation is y squared plus y, that's the product of 2 consecutive ones, is x cubed minus x, that's the product of 3 consecutive ones. And that gives us a nice affine model of an elliptic curve over Q. It's an affine model over Z. And let me call that Mordell's elliptic curve if I have to refer to it. Nice one. We know all of its integral solutions. And Mordell's original question is about its integral solutions. Now, integral solutions and rational solutions have sort of a different status, at least for elliptic curves. Because for any equation that equates a quadratic expression of a variable y to a cubic expression of x, there's actually an algorithm. There's a genuine algorithm for allowing you to find, and not only know whether it has a solution, that's what Hilbert was interested in, but actually finding them all. The algorithm explicitly given by Alan Baker. Namely, if you just take the maximum heights of the coefficient of this curve and call it h, then the maximum of the x and y is, well, it's a forbidding algorithm. Maybe we won't be able to find it. Maybe it's useless. But at least it's finite. Is less than x of...
Effective.
What?
Effective.
Well, it's effective. Yeah, it's there. It's not only finite, but it is explicit. It's explicit. Yeah. Yeah, perhaps one should brood a little bit about that and sort of making bounds, making a distinction between bounds that are realistic and bounds that are not. But it's a success. And the success is in contrast to the general problem as solved by Maciejewicz, and is in contrast to the problem of rational solutions, where even today we have a beautiful algorithm for computing all rational solutions of elliptic curves, and if I have time, perhaps I'll mention it on the board. I won't mention the algorithm, I'll give the structure of the algorithm on the board. But that's only conjectural, and it remains sort of seriously conjectural, and it will probably, one makes advances every week in it, but it's still conjectural. So we're going to Mordell, back to Mordell's equation, and ask for its rational solutions. Well, 0. 0 squared plus 0, 0 cubed minus 0, that's a good one. So 0, 0 is a solution. And the group structure will allow us to generate solutions from that 0, 0 using the chord and tangent process. And going to positive and negative exponents, one discovers that one has actually, by the chord and tangent process, starting with 0, 0, produced absolutely every rational solution of Mordell's elliptic curve just by chord and tangent process. Now, this produces an infinite cyclic group, and you can consider, say, the positive powers. And what I've done here is I've given you, actually, I've done it, I've done this more than once. And I realized that almost every number theorist who gives a general lecture about this equation can't resist showing the denominators of the x-coordinates of the various solutions that you get from the chord and tangent process starting from 0, 0, and these are they. Now these denominators are kind of interesting. Well, here they are, if you wanted small n in large type font. They, of course, start with integral solutions, 0, 0, 1, 0, minus 1, and they begin to creep up with their denominators there, as this slide sort of makes clear. But there's the shadow of a parabola here in the list of solutions, and there's something about that parabola. In fact, if you gave me the exact size of the type font, I can give you the equations of that parabola, which is kind of amazing. And the equations are simply determined by what's called the regulator of the elliptic curve. Okay. So now's the question. We have these x-coordinates which are growing, and they're growing sort of like Fibonacci numbers. So if you can use Fibonacci numbers to model the logic of the integers, why can't you use the x-coordinates of such an equation? Okay, so that's the question. And in fact, you could do that. Moreover, if, say, Mordel's elliptic curve is a Diophantine stable for some extension, L over Q, you can use those very same denominators to give a Diophantine construction of the ring of rational integers and the ring of integers of L. And therefore, you can convey the undecidability of the ring of integers to undecidability for L. So this is now an interesting industry. And actually, some of the theorems that I mentioned of Carl Rubin and myself, that's what we were working with and working for in order to apply to this logical situation. So in talking about the arithmetic of elliptic curves, I can't resist just mentioning some various pillars of the arithmetic of elliptic curves. There's one other thing which I feel I should mention, which I probably do have time for, so I will. Modular curves. Now, whatever they are, they seem to play two completely disjoint, I say somewhat disjoint, roles in the foundation of the theory of elliptic curves. So they're algebraic curves. They're algebraic geometric objects. The ones of interest are actually defined over Q. But they're of interest as well over the complex numbers or over any field, really. Okay? And they enter the scene as classifiers. They're moduli spaces. They tell you the parameters of a certain structure. And their points, or most of their points, determine elliptic curves with some extra interesting arithmetic structure, such as you might want to consider pairs of elliptic curves with a point of a fixed order n. N is fixed. You might want to consider those pairs. And that's a moduli problem, and the completed moduli space that classifies this is usually called x1 of n. It's given as a quotient of the upper half plane by subgroup of SL2Z, which I will write, called gamma 1 of n, and completed by the adjunction of a finite set of points called cusps. The point about it is that it's k rational points for any number field k, non-cuspidal points, give k rational pairs of elliptic curve and a point of order n. So if you're interested, for example, in points of order n, there you are. You look for points on that modular curve. The other role modular curves play is this famous modularity theorem, which is totally transverse. What it says is that any elliptic curve is covered by one of these modular curves. And the covering is by a map of finite degree. And so any elliptic curve over Q, is covered by one of these elliptic curves. Over Q is important. And what does that mean? That means that if you have any elliptic curve over Q, up to finite ambiguity, it knows all elliptic curves. Let us say you take a point on that elliptic curve, take its inverse image in this modular curve, you get a finite set of points. That finite set of points classify a bunch of elliptic curves with extra structure. And as you vary the points of your elliptic curve, you're moving over this moduli space. So any elliptic curve over Q knows, in some sense, up to, as I say, up to finite ambiguity, an awful lot of structure regarding all elliptic curves. This is a very strange interrelationship between two aspects of the same creature. Okay, the other classical pillar is much older. It's 1922 is when it was introduced. It's the Mordell-Bay theorem. Oh, 1922 was the theorem of Mordell, and extended by Bay a little later. And it says that that group of elliptic curves over any number field is a finitely generated abelian group. Finitely generated abelian groups are characterized up to isomorphism by the isomorphism type of its torsion subgroup and its rank. That is to say, any finitely generated group can be written as the direct sum of a finite group that's in blue there, and z to finite power, which is in red. Let's say its torsion, which I'll call T of ek, and its rank that I'll call R of ek. The minute you have this theorem, you really have two research projects ahead of you, namely to study the behavior of torsion as a function of the elliptic curve and the field, and to study the behavior of rank. And I'll talk a little bit about both of them. So torsion has, in some sense, the issue of torsion is much older than the issue of elliptic curves, because it appears already in the work of Poncelet. It's a game of Poncelet. One thinks of it as a billiard game, where you have two conics in the plane. I'm thinking of the outer conic as the billiard table, and the inner conic as some sort of obstruction. And now you want to play billiards. That is to say, you start at some point of that outer conic at the edge of the table, and you make a shot, and the shot is meant to graze the obstruction. And when it bounces, your billiard table is so organized, who knows how, so that when it bounces with a chord that also grazes the obstruction, and you keep going. Now, sometimes your shots will be everywhere dense, but sometimes they will close up, such as that star there on the picture. Now, Poncelet noticed that if you start at any point on your table and it closes up with period n, start at any other point of the table is going to close up at the same period. So that was what he noticed. What we would notice if we're elliptic curve people is that a pair of conics is quartic, and and quartics also represent elliptic curves appropriately. And what this pair of conics, such a pair of conics gives you is not only elliptic curve, but an automorphism of it. And the automorphism is either of infinite order or a finite order, and that's what determines the game of Poncelet. But there's an immense literature about the time of the French Revolution about this. Anyway, that's torsion. Torsion over Q. Torsion over Q is really an arithmetic issue, and we have a complete classification of torsion over Q. And here's one way of stating it I'm stating it in a Serge Lang sort of way, in a minimalist way. The isomorphism type of a finite group T occurs as the rational torsion group of some elliptic curves over Q only when it's forced to recur by algebraic geometry. Now, what in the world does that mean? That is to say, only when the modular curve classifying pairs consisting of elliptic curves together with a specific finite group isomorphic to T is isomorphic to the projective line over Q. Therefore, if there's an isomorphic to the projective line over Q, of course, you've got not only one rational point, but you have a whole family of rational points, a rationally parametrized family. In other words, torsion only over Q only comes because of and from rational parametrized families. Okay, that's interesting. And then, of course, you have infinitely many examples. So you never have one example of torsion over Q. You have infinitely many examples. Now, what about number fields? Where are we in this same problem for number fields? Well, I'll fix a positive integer d, and I'll let p be the largest prime number such that there's an elliptic curve defined over a number field of degree, I have less than or equal to d, say degree d, for which there's a point of order p on that elliptic curve rational over that field, and we'll consider the various data points for this. There are bounds. The lower bound, d to the 1/2, is trivial. It's because the modular curve that parametrizes such a thing maps to the projective line by roughly a map of degree p squared, and so you get a d to the 1/2 there. The upper bound is extremely deep, and it's a theorem of Merel, and improved by the bound is improved by Osselet and Parent. And here you're looking at a lower bound that's polynomial, an upper bound that's exponential. Which way is it going to go? Is it going to be polynomial or exponential or somewhere in between? Now, if you're sort of a certified minimalist, you would certainly be willing to ask that question that I put down below, and I ask it. I wonder whether it's very close to the fairly trivial lower bound. Now, what about data? We have a generation of absolutely fantastic computers. They're, computers meaning people. These guys are really good, and they're really young too. Anyway, there we go. So Martin Derricks, and I don't dare pronounce his name. I think it's, I don't know. Okay. It gives a log-log plot of the data points of primes and degrees. Okay? Here it is. Now, if you look at the blue, that's down below, that's down very close to the lower bound. If you look at that red curve, that is the upper bound. Okay? The red curve? Is there no red curve? Green. Oh, maybe I have that guy.
Green.
Oh, is that green? Is that green? It's red here. I am colorblind, by the way, but not that colorblind. Okay, the green curve. Green. Okay, that's the upper bound. And the blue is the lower bound. And so every x is a data point. And here are the data points. Now, the red x's are really interesting. You'll see why in a sec. Okay. So, if you have a p and a d, and you have a map from x1 of p to the projective line of degree d, you get a whole parametrized family of these guys. Yeah. So I'm not interested in them. These are algebraic geometry, in a way. So let's call a point of order p over a number field of degree d sporadic. I'll want d to be the smallest number field over which that point can be defined. If it doesn't occur because of algebraic geometry, if it doesn't occur as a member of a family, if it's a kind of sporadic gadget. So Martin Derricks and Sheldon Camieri and I have this project of trying to see what we can do about this. And for d equals 1, there's the classical theorem that there are no one sporadic points. For d equals 2, that's the theorem of Sheldon Camieri. 4 is what we're working on, and we haven't totally written it up. We believe there's no 4 sporadic points. The largest prime that occurs is 17. And it's an interesting situation where there are going to be essentially 3 rational families coming from giving points of 17, and that's all there will be up to automorphisms. And the other thing to say is this is interesting for experimentation. I mean, people should, who are interested in computing, it would be very nice if people who are really sort of focused in computing might help us with that. Let me go back to the picture. Those red points are sporadic, and every one is a computational success story. They're very hard to find. Anyway, okay. So we're not yet ready to make any conjectures about that, especially in relation to the d to the 1/2 plus epsilon conjecture that I hinted at before, but possibly we'll make more explorations. Okay. So much for torsion. What about rank? Okay. So let K be a fixed number field, and consider all elliptic curves over K. So really, the first question you might ask of a statistical nature about more arbitrary rank is, does it admit a finite upper bound for a fixed K and all elliptic curves over that field K? And, well, I certainly thought the answer was no, but I think I may have been forced to change my mind, or maybe not yet, but because as you see in the bottom thing, I hope you can see it, recent news-breaking heuristics of these people, Jennifer Park, Bjorn Kuhnen, John White, and Melanie Wood, they use certain statistics about Lagrangians and Selmer groups, and they come up with the most astounding conjecture. And I checked with all of them that I can say it, because they're working on it. They say they're working on it, and they think, but can I say it in these lectures? Bjorn Kuhnen says yes, and I said, well, check with all your co-authors, and he come back and said yes. So, okay, here's their conjecture. That 21 is the largest rank that one would expect to have infinitely many elliptic curves over Q of rank 21. From then on, 22 and so on, for each number, there may be finitely many elliptic curves with rank that number, but not infinitely. It stops at 21, and they have a sort of rather daring conjectures for not only Q, but for any number field. Okay. So let's take a look at the rank so far. So 21, that's 1994. That's, now the 22, 23, 24 examples, therefore, if the conjecture is true, each one of them is an example of finitely many of that rank. If Bjorn et al.'s conjecture is true, which is quite interesting. As for the 28 example, which is due to Elkies, take a look at the coefficients of that elliptic curve. It's a tough business to actually compute.
What's the biggest of a QT?
Yeah, I don't dare say. I don't know. What? Yeah, no, it's not. Sure. Yeah. So what can knowledge of Borel ranks of elliptic curves over large fields of algebraic numbers get you? So I want L to be a large subfield of the field of algebraic numbers, and E an elliptic curve over L. Now, the theorem of Schlappentag tells us that all you have to do is find an elliptic curve over that field such that its group of rational points is finitely generated and yet is of positive rank, then there's a first order model of Z in that ring of integers. First order model as we discussed in the first lecture. So we get first order undecidability for these fields. So the theorem with Carl Rubin is, in fact, you can find loads of these, that is, say, thanks to Diophantine stability, of course. There are uncountably many subfields of the field of algebraic numbers in QP for which E of k is finitely generated. And so for these, you get that Z is first order definable. That is to say, there's a first order model of Z defined in K, as we discussed some minutes ago. And so therefore, any of these subfields is undecidable. Now, in Friday's lecture, I'm going to actually give the methods of proving these things. They're very far from the conjectures that we hope is true. As I mentioned briefly in the previous lecture, that I say, here's a conjecture that lets E be an elliptic curve over a number field K and L just a large prime, greater than, well, depending upon the X through the E. Depending upon E and K, then statistically, for 100% of the cyclic extensions of degree L over K, we have Diophantine decidability. Now, we have no method of proving this. I mean, if one thinks of how one might think of this situation for L equals 2, where one sort of has this kind of metaplectic automorphic mechanism to sort of deal with it, it's staggering to imagine what type of metaplectic automorphy one might need to apply to actually prove this conjecture. But in any case, it is a conjecture that I think I feel confident in sort of asking. And more generally, the same thing for curves. X could be, if X is an irreducible curve of positive genus, and L is large enough, then the same thing is true. It doesn't, for 100% of the cyclic extensions of degree L over K, we have a Diophantine stability. And possibly the same thing is true for projective varieties. That is to say, if you have any projective variety, and any, for a large enough prime number, one of these two things will happen. V contains the image of a projective line, or for 100%, it will be Diophantinely stable. Okay, thank you. On Friday, methods.
So I think we have time for a couple of questions. Always, I think you partly answered a question that I've always had.
What's
Somebody
that?
should write, explain unreasonable effectiveness of modular forms and elliptic curves in number theory.
Unreasonable effectiveness.
Yeah, because they don't have the right to play such a big role. Apparently,
Yeah.
you make quite a good case here for certain things. And, it's hard to explain before you start why a general equation might require why an elliptic curve plays.
Why does an elliptic curve, why do elliptic curves or modular forms or abelian varieties play such an
Maybe you could write a paper called The Unreasonable Effectiveness.
unreasonable effectiveness of abelian varieties? Okay, yes. Okay.
One error be
What? L big? Not so big. In fact, on Friday you'll see it's not that big. No, you need L to be, L better be congruent to one mod a bunch of things. Well, no, let me be a little more specific. One will be passing, this is in terms of the methods, we'll be dealing with algebraic groups. And you have an algebraic group. It's a sort of honest algebraic group, but we'll need to know the points over finite fields of degree L of that algebraic group. And it's only when L is very, very large that you can sort of, in some sense, guarantee that those points are themselves an algebraic subgroup of some general linear group, and you play with it. Up to finite index, up to bounded index, then the bound is independent of L. So you have various bounds that are independent of L, and you have to deal with it. But I should say, I'm not going to get into the details that precisely on Friday. It's going to be a general flow chart of the method.
Question.
I'm interested to know if there are any modern facts which were known in the language of Poncelet.
Any in the language of Poncelet? Well, you know, any modern facts beyond the torsion issue.
Yeah. About torsion points.
Oh, did he know anything? He constructed examples.
Something which could be translated in the modern language. Some information about torsion points which could be translated.
I suspect not, except for actual constructions. I mean, he loved those constructions.
I think I once looked up who was the first to understand that the billiard ball inside an ellipse is integrable. That is, that you take the confocal ellipse, you always tangent. Boscovich. I spent a lot of some Latin thing. Presumably you could do it. I didn't know. Because it's a remarkable thing.
That it's integrable. Yeah.
And which is closely connected to this.
Yeah. Okay, thank
all right,
you.
well, there'll be the third and final lecture tomorrow.
No, Friday.
Friday, same time, but Barry's around, and he's in Dave Gabai's office, and you can ask him private questions if you need to. Thank you.